Dear Professor, today I will explain a step counting algorithm that uses all three axes of accelerometer data to detect steps. The program is designed to be efficient, accurate, and adaptable, providing reliable step count for a 5 minute interval. The first is about program structure and workflow. The algorithm processes acceleration data from the x, y, and z axes sampled at 50 Hz. It identifies step-like patterns using a combination of signal processing, peak detection, and adaptive thresholds. Let me explain each part of the program in detail, following the sequence of execution. The first is about reading and processing acceleration data. The program first reads raw x, y, and z acceleration data. Since walking or running cause periodic motion in at least one axis, the algorithm simplifies the data by calculating the sum of absolute values is MOD of the three axes. Is about this part. Then we can take low-pass filtering. So I created a function which is called low-pass filter to eliminate noise from irregular motion or sensor artifacts. The MOD signal is smoothed using a low-pass filter. This filter averages the last four samples stored in a circular buffer. And let's move on. The third part is about peak detection. Peaks in the filtered signal represents the walking cycle. The algorithm alternates between detecting maximum peaks and minimum peaks. A peak is considered valid only if it is the highest or lowest value within a time window centered on a sample. For example, in order to find the maximum, we use this part. This ensures the detected peaks accurately reflect step motion. And the next part is about dynamic thresholding. To distinguish real steps from random fluctuations, the program calculates a dynamic threshold. This threshold adapts to the user's movement by averaging recent peak values. A peak is classified as a valid step only if this part be finished. The sensitivity margin helps filter out small fluctuations caused by noise or non-step motion. And the last function is about step validation and regulation mode. The program requires 8 valid steps in a row to confirm the user is walking or running. Once this condition is met, the program enters regulation mode, where all the subsequent steps are directly counted, just like this. And this part. This ensures the algorithm avoids false positives caused by isolated movements. And finally, we got a data logging. The program logs important information, sample numbers, MOD values, and total steps to a CSV folio for debugging or further analysis. And then we consider about the algorithm logic and performance. The steps counting algorithm follows these steps. The first is data input. Acceleration data is sampled and the MOD is calculated. The next part is about signal smoothing. A low-pass filter removes noise. And the third part is peak detection. Local maxima and minima are detected within time windows. And the fourth part is about thresholding. Dynamic thresholds validate significant peaks. And the last part is about step counting. The time window for a peak detection are carefully chosen to capture walking and running. This ensures accurate detection across different speeds. So let's get some conclusion. This program effectively combines signal smoothing, adaptive threshold, and steps validation to provide accurate step count over a 5-minute interval. It uses all three axes of accelerometer data, making it robust to orientation change and noise. The program is well structured and reliable for real-world applications like fitness tracker or wearables. Thank you, and I'm happy to answer any questions.